Hello friends, so I welcome you all to the second lecture of module of week 11 of soil and water conservation engineering, and in the last class we have seen about the wind erosion, its definition, and what are the different control measures are there to reduce the erosion due to wind. So, let us see the okay. So, this is the second lecture of this week 11. So, in the first lecture we have seen the process of wind erosion, the definition of wind erosion, different movement of the soil particle, or whether it is like detachment of the soil particle from the surface in the process of initiation. Then we have talked about transportation, deposition. We have talked about the soil particle transport through various transport of soil particle movement through like saltation, suspension, and surface creep, depending on the size of the particle and the grade of the soil particle. Okay. So, we have also seen the various ways or various factors that influence the various ways which influence the erosiveness of wind, different factors that controls the wind erosions. Okay. And we have identified the parameters which can be used, which can be modified to in order to which we have to modify in order to reduce the effect of wind erosion. So, such as by reducing the wind speed and by making the soil surface cover more resistant to the wind erosion. Okay. So, in this present class, in today's class, we will be understanding the wind breaks which are mostly used to reduce the effect of to reduce the wind speed. Okay. So, let us start this class. So, wind break can be defined as any barrier that can be used to protect the any type of barrier which can be used for protection from the wind. Okay. So, it is any type of barrier which can be used for protection from wind, and it is more commonly associated with the mechanical or vegetative barriers for buildings, gardens, orchards, and feedlots. Okay. So, what does they do? Okay. So, this we will see that in the next slide. Okay. So, this slide shows the function of wind breaks. Okay. So, the wind break, they reduce the surface wind, they slow down the wind, and they absorb the higher magnitude of wind velocity and deflect the high or erosive winds to another direction. So, so we can say that they slow down the wind or they reduce the wind speed, and they redirect the wind, which will modify the microclimate and microenvironment that may be favorable for crop growth. Okay. So, modification in microclimate or environment may or may not be sometimes it is favorable or not favorable, but we have to design the wind break in a such a way that we get maximum benefit from this. Okay. So, this modification in microclimate includes such as it can improve the ecological aspects. Okay. It can enhance the biodiversity, or it can improve the ecological aspect or that region, or sometimes when we use some irrigation method such as sprinkler, which does not require a very high wind speed. Okay. So, okay. So, sometimes we use sprinkler irrigation in which very high wind speeds are not desirable. So, by placing a proper wind break, we can reduce the erosive power of wind, we can reduce the wind speed, and the effectiveness of irrigation can be enhanced. And sometime also, such as like in other irrigation methods, because of the wind erosion, the wind or dust may get soil particles may get deposited over the irrigation channel or drainage lines. So, we need a lot of maintenance operation is required. So, by placing a proper functioning wind break, we can reduce the maintenance cost. Okay. So, So, let us see the effectiveness of windbreak based on its structure. Okay. So, when I say structure, it means the density of the windbreak, then height of the windbreak, length of the windbreak, its orientation with respect to the prevailing wind or dominating wind direction, then continuity, whether it is continuous or some gaps are there, then which kind of species or sub combination of species we are choosing for the windbreak, and number of rows, that is the arrangement which is used. So, these all factors that determines the overall effectiveness of the windbreak. So, we will be looking these parameters one by one in the next slides. Okay. So, first the height. So, height of the windbreak is actually defined. So, let us say suppose so we are planting windbreak here. Okay. So, the height is defined by height of tallest row of trees. Okay. So, in case of suppose you are planning for multiple row of windbreaks. Okay. So, the functional height of that windbreak will be height of tallest row. Okay. So, height of tallest row is actually the height of that windbreak. So, that is the height which can be which is a design height, and it determines this importance of the height is like, because this height determines the downwind length of protection. So, for example, by placing a windbreak over this region, okay, suppose if you are placing some windbreak here, okay, so the height of this windbreak determines the length, okay, so the height of the windbreak, okay, determines the length of protection downwind to this windbreak. Okay. So, in that case, in that sense, height is very important parameter. Okay. So, the effect of height we can see here. So, suppose this is some kind of wind barrier, one cross section of wind barrier, and this is some kind this is height h, let us say this is height h here. So, the effect of so purpose of windbreak is to reduce the wind speed. Okay. So, our desired area is this one. Okay. So, we are planning for leeward side of the leeward side of the windbreak. Okay. So, what we can see, if the height of this windbreak is h, okay, so we can get maximum reduction of the wind speed till at a distance of 10 to 20 h, means 10 to 20 times height of this windbreak. Okay. So, the effect of wind reduction are measurable till a distance of 10 to 20 h from this windbreak. Okay. So, sometimes if you place a proper arrangement, or sometimes if you use proper combination of high density and with low spacing species, you can achieve protection of around 30 h also. Okay. So, not only on the leeward side, but on the windward side also we can see there is a reduction in the wind speed, and this reduction is visible, this reduction can be visible till the height till the length of 2 to 5 times height of the windbreak. Okay. So, both on the windward side and leeward side we can see the effective wind speed reduction. So, but here we are planning for the leeward side. Okay. So, similarly, in this example, in this figure also you can see, which is taken from Schaub et al. 1971. Suppose this is the windbreak. Okay, this is a windbreak, and here this numbers actually represent the percentage of normal wind. So, when I say the 50 here, so what does 50 mean here? So, wind speeds are here like 50% of the normal condition wind speed. So, there is a 50% reduction over this region. Similarly, over this region you can see there is a wind speed is around 50 to 60% of the normal condition. So, it means there is a reduction of 40 to 50% reduction. Here the reduction is 30 to 40%. Similarly, here reduction is 10 to 20%. So, what you can see, so most of the protected like effective protection area you can see at the length of 10 to 20 h. Okay. So, here we can see the most of the effectiveness is visible till around 17 h length. Okay. Once you go away from that, you can still measure some kind of reduction, but the reductions are very less here, around only 10% reduction. Similarly, this is the leeward side. Okay. This is the leeward side and this is the windward side. Okay. On windward side also you can see, so there is a reduction in wind speed of around 10% reduction here. So carefully, if you see here over this region and this region, which are actually at the very near or adjacent to the end of this windbreak. So you can see the velocities are here are 110 to 120%. That means the wind speeds are actually very high compared to the open field. Okay. So here the wind speeds are very high, because what happens when you construct or when you design and when you plan a windbreak here and when you construct a windbreak here. So our objective is to stop the wind or to reduce the wind speed, but it forms a low pressure area over these regions. So because of this low area formation, so wind from the neighboring side will rush to fill that low, and the wind speed will get increase over this region. Okay. So these are the regions where we get maximum amount of maximum speed. So you need to be very careful while deciding the length of the windbreak. So this will be discussing in the next subsequent slides as well. Okay. So now here we are discussing about the height. So most of the effect is visible till the height around 10 to 15 H. Okay. Now length is also very important parameters, because it determines the amount of area which will be under protection. So suppose for this windbreak, so this will be the area. So in the last slide we have seen the area of protection for that particular length. Okay. So length is very important parameters that determines the amount of area will be covered, will be protected. Okay. The length should be longer than the length of field. So when you are designing a windbreak, the length of the field, okay, so the length of this windbreak should be longer than the length of field. So ideally there should be continuous long rows should be preferred. The continuous long rows should be preferred because they provide greater area of protection, and generally this length should be at least 10 times the height of maximum height of windbreak. Okay. But that depends on your requirements again. Okay. So in case if the length is not enough, you can place you can increase the length so that the area of protection can be increased. Okay. So as I said earlier, the length to height ratio of the windbreak should be 10:1, because by maintaining this ratio, you can reduce the influence of end turbulence on the total protected area. So in the last example, we were seeing that Okay. So in this example, what we are looking that effect of length we can see here. So over this area, if you can see, if the length is not sufficient, so the wind speeds are very higher. So if your length is very short, then this erosive wind can damage, then they can cause more damage to your field. So the length should be at least 10 times than the height of windbreak. Okay, so it means for 1 meter of windbreak, height of windbreak, you need at least 10 meter length of windbreak. Okay, so here you can see the so here over the ends, this is the end effect actually you can see. So wind speed are increased around end of the windbreak by amount 1.1 to 1.3 times than the open area. So here, as I said earlier also, the winds are very high speed here. So your effect, the length of design length should be more than the field length for which you are going to give the protection. Okay. Now continuity. So this continuity is actually very important because it determines the effectiveness or efficiency of your windbreak. Okay. Okay. So this is an example. This figure shows the effect of continuity. So suppose this is a windbreak. Okay, and it has some break in between. So this is some gap in between. So because of this gap, there is an increase in wind velocity. So, these numbers represent the percentage of wind velocity compared to the open wind field condition. Okay. So, here the wind speeds are more than the actual wind speed in the open field, that is 100 to 120%. So, if you would have construct the windbreak, a continuous windbreak, then we would have achieved a greater reduction in wind speed over this region. But because there is a gap here, so the winds are coming in, winds are approaching at very high speed here, and the effect of wind speed, effect of windbreaks are less over this region. So, so here also you can see the effect is around like only 20% reduction is there. Here you can see the reduction is quite well around 60 to 80%, because the wind speeds are around 10 to wind speed around 20 to 40%, but effectively because of this gap, the overall protection area, the effectiveness of windbreak has been reduced. Okay. So, the care has to be taken that gap should be avoided, and suppose if it is unavoidable, if you want to place some kind of gaps in between to allow some access lane, so in that case you can think of choosing multiple rows of windbreaks, so that and the access lane can be provided at some angle to the prevailing wind direction. Okay. So, the effect of gap can be minimized, and effectiveness can be still achieved. Okay. The next is the orientation. So, first designing windbreak, you should know the prevailing wind in your area. Okay. So, what is mean by prevailing wind? So, by prevailing wind we mean that maximum probable wind direction for your field, okay, over a year. So, once you know that predominant direction, you can plan your windbreak in direction perpendicular to that direction. Okay. So, in the next slide we will see that. So, orientations of the windbreaks are most effective if they are placed perpendicular to the prevailing wind. So, once you know the prevailing wind direction, so the placement of windbreak should be perpendicular to the perpendicular direction of prevailing wind. So, you can get maximum amount of wind speed reduction over the downwind area or leeward side. Okay. So, sometimes when we say when you know the predominant area, but it is not always true that that wind will only flow in that direction, because wind is a climate variable, and it's a variable that often changes its direction as well as its magnitudes under the influence of large scale processes as well as local scale disturbances. Okay. So, winds direction and magnitude changes, but predominant direction will remain same. So, what you can do, you can place one windbreak over a direction which is more predominant, across a direction which is more predominant, and another windbreak to any other direction where the effect of you may feel that the wind direction may change. So, you can think of multiple windbreaks, multiple leg windbreaks to increase the area protected. Okay. Then another thing is the kind of species which we are choosing for the windbreak and number of rows. Okay. So, in order to select a windbreak, we have to choose a species or combination of some species in such a way that they are more they are favorable to that climate, or they can sustain over that climate, and whatever our design objective is there. So, whatever amount of reduction in wind speed, or let us say for snow or protection from cold wind we want. So, that kind of thing can be decided by selecting the proper kind of windbreak species, tree species, and then the number of rows. Okay. So, number of rows sometimes depends on the requirement or space constraint, you have to decide on the number of rows. Okay. Now, another important parameter is the density of the windbreak. It is the most important parameter which actually affects in combination with height and length, it affects the overall protected area, the extent of protected area. Okay. So, the density is nothing but the percentage solid, or it's a, we can in general use you can say that it's a ratio of open portion of the windbreak to its total volume. Okay. So, as I said, the height together with density and length determines the overall effectiveness of wind speed reduction. Okay. And of course, the length of protected area. So, density is the most important parameter here, we will be seeing in the next slide as well. Okay. So, before going further, let us see the wind speed profile. Okay. So, we know that when there is an open or bare surface, so bare surface does not have any roughness. So, the wind speeds are increasing by a factor of logarithm of height. So, wind speeds are slowest here, but when you go up, the wind speeds are increasing by a factor of proportional to the logarithm of height. And but if some roughness is present over the ground, then there will be some disturbance, there will be some turbulent flow, and there will be some eddy motion. Eddy motion means there will be some deviation from the mean flow. Okay. So, that causes some turbulent motion. Okay. So, this is some basic term that I was trying to mention here. Okay. So, now we will see the effect of density. So, let us say for a windbreak we are placing a solid barrier here, which actually has close to 100% density. Okay. So, it is not allowing any air to pass through it. Okay. So, it is the porosity is very less. Okay. So, what happens when the very high wind velocity strikes here? Okay. So, what happens? So, when very high wind speed velocity strikes here, so it is not able to pass through this solid barrier, and there is a formation of pressure eddy over this region. Okay. So, because of this formation of pressure eddy, so we can see some reduction in wind speed also here. So, this effect of pressure eddy can be visible to the distance of 1 to 2 h on the windward side. Similarly, on the leeward side as well, if you see, because of this solid barrier which is not allowing air to pass through it, so winds are very high in motion, they are getting deflected here, and because since there is no air movement, not air movement in the sense like air is not passing through this solid barrier. So, there is a very low pressure formation of low pressure over this region. So, to fill this low pressure, so the winds rush over this region with very high wind velocity. So, this region is known as the suction eddy. Okay. So, this will form a suction eddy whose effect will be visible till a distance of 1 to 3 h. Okay. So, because of that there will be lot of turbulence, and this is a turbulent wake zone which can be seen till the length of 6 h, and after that there will be resumption in open field flow velocity. Okay. So, what it means that because of this low pressure formation here behind the solid barrier, the windbreaks pulls the air coming over the windbreak downward and creating turbulence and reducing the protection downwind. Okay. So, the effectiveness of the windbreak will be or effective or extent of area under protection will be reduced. Okay. Now, let us replace that solid barrier with the porous barrier. Okay. So, let us say we are planting some porous barrier here. So, let us see what happens. So, since now this porous barrier is allowing some air to pass through it. Okay. So, there is a moderation in the air flow here. So, the effect of pressure eddy will reduce. So, on the windward side. Similarly, on the leeward side, because now air can pass through it, okay, not like in case of solid barrier there was very less flow, but here actually air can pass through it. In case of solid barrier, sorry, it was the flow was not there actually, it was non-porous, but here in case of porous barriers the winds can pass through it. So, so there is a modification in the wind flow here. So, here the density of this now as the density of this porous barrier is decreased, the amount of air passing through the windbreak is increasing. So, it is allowing more air to pass through it, and it moderates. So, by allowing by allowing more amount of air passing through windbreak, it moderates the low pressure and turbulence and increasing the length of downwind protected area. So, the lower left of section AD, so what we can see here, because of this porous media, the length of downwind protection can be increased. Okay. So, here the turbulent wake is further downward as compared to the solid barrier here. Okay. And resumption to the open field flow condition are further shifted to the farthest away. Okay. Now, this diagram shows the effect of wind speed reduction if you are using different kind of layers, permeable layers, moderately dense layer, permeable layer and very permeable layers. Okay. So, let us say this is our the wind barrier or windbreak in the form of windbreak or shelter belt, let us say, and on x axis we have wind velocity relative to the open condition, and on x axis we have distance from the wind barrier. So, this is our wind barrier. So, this is our windward side and this is our leeward side. Okay. So, what we can see when the layer is actually highly impermeable, that is which is represented by this solid line, sorry. So, this is the solid line which is represented by solid line here. So, when the barrier is impermeable, that means it is not allowing air to pass through it. So, we can see till the distance of let us say 5 to 7 h, there is some significant amount of reduction in wind speed, but when you go away from this distance, so there is not such very much reduction in wind speed. Okay. Then contrary to that, if you see a very permeable, so in permeable there is not significant change. Okay. So, at very near to the windbreak, the wind flow condition was around like 90%, let us say 100% here, this is open flow condition, and near to let us say for 7 h or 8 h, it is around 60 to 70%. So, there is not much change. So, the effectiveness of this windbreak is depending on the porosity or density of this what kind of material, what kind of species we use as a windbreak. So, if we use moderately dense and permeable, so we can achieve maximum length of protection here. Okay. So, this we'll see in the next slide as well. Okay. So, yeah, say here again this shows this figure or this slide shows 4 cases in which we are varying the density. So, in the first case, that is A, so we are using deciduous tree which is having 25 to 35% density. In the case B, we are using 40 to 60% density of by placing conifer tree. In the case C, we are using if you want to suppose increase a multiple, if you want to use multiple rows. Okay. So, let us say our density is 60 to 80% here by placing multiple rows of conifer tree, and by placing a solid fence. So, let us say there is 100% density. So, what is the effect on wind speed reduction? Let us see that. Okay. So, in case of first case, when we are placing deciduous tree with 25 to 35% density, so we can see at a distance of 5 h around 50% reduction is observed, whereas at a distance of 15 h we can see the winds are 80%, means 20% reduction is observed. So, here at the distance of 20 h the wind speeds are 85% compared to the open field, it means the 15% reduction, whereas at the distance of 30 h the winds are normal to the winds are similar to the open field. Okay. So, we can see the effectiveness of this wind effectiveness of this windbreak in reducing the wind speed can be observed till 20 h. Okay. Similarly, in the case B, if you see the density is 40 to 60%. Okay. So, the density is 40 to 60% here. So, in that case, so for a distance of 5 h, you can see there is 70% reduction, whereas at a distance of 20 h there is a 25% reduction. So, which is very higher than this less density windbreak. And we can also see over a distance of 30 h we can also have some 5% reduction in wind speed, whereas in case of in case of multiple row with density, multiple row of conifer trees with a density of 60 to 80%, we get almost similar to that to that of the case B, but slightly improved. But over the 30H we get almost similar reduction. Okay. So, its effect is most visible near to the windbreak. So, here 75% reduction as compared to the 70% reduction here. Whereas, in case of solid fence, that is 100% density, we can see, so maximum density we can achieve here 25% near to the windbreak, whereas when we move away from this windbreak, so at the height, at the distance of 20H we can only get 5% reduction, whereas in case of conifer tree it was 25%, in case of 20H 25% deciduous tree it was around 15%. So, here in case of solid fence we can only get 5% reduction. Okay. So, the windbreak density of 40 to 60% provides a greater downwind area of protection and provide excellent soil erosion control measure. Okay. So, now let us see how it is modifying the microclimate. Okay. So, since the wind speeds are reduced here, so it can modify the air temperature, soil temperature, relative humidity, daytime air temperature, nighttime air temperature, heat loss, etc. These are the parameters that can be affected by the by modification of microclimate because of the reduced wind speed. Okay. So, this is a very important figure. So, here we can see on the x axis, on the y axis we can see percentage of control, that means percentage. So, by placing barrier values by placing barrier multiplied by 100 divided by values that are there in the open condition. Okay. So, this is again the upwind side, this is downwind side, and these are the different variables, crop yield, soil moisture, air temperature at day, soil temperature at day, relative humidity, air temperature, evaporation and wind speed. And along x axis what we can see here is the measured length of protection. So, what we can see here, so we can see the high amount of temperature and humidity because of placing this windbreak, and there is a reduction in evaporation. Okay. So, we can conserve more moisture here and plant water loss is also less. So, because this daytime air and soil temperatures are more, but the increased relative humidity actually increase in relative humidity and soil moisture, because we can conserve more soil moisture here, combined with decreased evaporation, it results into the higher amount of crop yield. Okay. Okay. So, this is how a particular windbreak with particular density it modifies the overall microclimate over that region. Okay. Okay. So, to summarize that, so our goals for designing any windbreak should be, so design consideration by considering density and placement, this should be based on different goals. So, our goals can be either to have to increase the crop production or for crop production, or to reduce soil erosion, increase snow capture in the field, or for farm street protection, or a living snow fence or a sound barrier, or for a wildlife for food cover. So, there are different objectives, and accordingly for different objective we need to modify the different density, different structural conditions. Okay. So, with that I will stop here for this lecture, and in the next class we will be looking at the design of shelter belts. Okay. Thank you.